Hello everyone. This lecture 6 of course PE 645. In the previous lectures we have covered multiple handcrafted features such as GLSZM and GLRM and also first order features, and all of that are in the second stage or phase of the radiomics workflow that consists of 6 steps, starting from acquiring the dataset until we reach high performance model and explainable model so that you can trust your model. And to recap again, what we are extracting right now for the handcrafted features are categorized in 3 categories: first order, second order, and higher order. For the first order, we are handling the pixels themselves, such as getting the mean and variance. Second order features, such as extracting GLSZM and GLRM, deals with the relationships between the current pixel and the neighbors. And for higher order features, we are using transformations or filters, which are considered more complex mathematical approaches. We still in the second order features. We covered GLSZM and GLRM, and in this lecture we will cover also a third technique called gray level size zone matrix or GLSZM. And this technique is a sophisticated and valuable method, and we can use it in image processing and texture analysis. And this method is specialized in extracting detailed and quantitative information about the texture and structure of the image, making it highly relevant in different fields such as medical imaging and material science. And the core concept of this technique is to represent the size distribution of the connected regions or zones that share the same gray level within the same image or the volume if you are dealing with 3D volumes. And a zone here means a group of contiguous pixels that all have the same intensity value. So consider that we have an image like that, and we found that all of this region has the same intensity value, so this can be considered a zone. And this technique represents the size distribution of these connected regions. So if you have 3 connected regions, 1, 2, and 3, we need to extract features from these regions. And capturing the regions requires something called connectivity. And connectivity here means which way are we looking for the neighbors. So if we have 4 connectivity, then we are looking in the horizontal and vertical direction. And if we have 8 connectivity, then we are including also the diagonal connections. So if you are here with 4 connectivity, then you are looking here, 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 and here. And if you have 8 connectivity, you will also include the horizontal, vertical, and also the diagonal connections. So you will check the neighbors around you in the 8 directions. Similar to the previous 2 techniques, GLSZM and GLRM, this technique also requires 3 parameters to facilitate the calculations. The first, which is familiar right now, is called N, is the number of gray levels, and this will indicate the discrete intensity levels present in the image. And Z, which is the maximum zone size. If we remember, in the GLRM, we got R, which indicates the maximum run length. Here we have Z, the maximum zone size. And here we refer to the maximum number of zone sizes required to build the matrix. Simply, Z can be calculated by multiplying the width by the height for 2D and width by the height by the depth for 3D. And this is simple because if you got an image that got all of the pixels, for example, with 2 or 3, then we have a big zoom that captures the whole image. And in this case, the Z value will be the width multiplied by the height. So simply, Z can be calculated automatically by default, width by the height for 2D and width by the height by the depth for 3D. The third parameter is called C, connectivity, and we illustrate it from a while. Here, C, we determine here what directions are we looking for. For example, in 2D, if we define 4 for the C, then we are referring to the horizontal and vertical directions. And for 8, we are including here also the diagonal connections. But in 3D, we have 6 connectivity and 26 connectivity. And we are going to illustrate these 2 values, 6 and 26, when we reach the 3D slides in this lecture. So, to deal with the GLSZM matrix, we require 2 steps. The first step is to create the matrix, and the second step is to extract the features from this matrix. So, as usual, you are creating an empty matrix with a specific size and start to fill this matrix and incrementing the different cells based on the technique. And by the end, we will get a filled matrix. We can extract the different features from it. N here refers to the unique discrete values, which are 4 because we have values 0, 1, 2, and 3. And let's assume that we are dealing with C equals 8. 8 connectivity means horizontal, vertical, and diagonal directions. And Z, as we mentioned, it will be calculated automatically, the width multiplied by the height. So we have 5 by 5, which equals 25. But let's set it for now to be 10. And I will illustrate why 10 after a couple of slides. The initial step is to create an empty N by Z matrix, which in our case will be 4 by 10, 4 rows and 10 columns. The rows refers to the gray levels and the columns refer to the zones, and all of the cells are initialized by zeros. As noted, the rows indicate the discrete intensity levels, the columns indicate the size zone, and we will start to loop on all of the pixels one by one, and for each one we will find the biggest zone that we can reach according to the 8 connectivity. So let's begin. For the first pixel, which is 1, we will try to find similar pixels with the same intensity values in the horizontal, vertical, and diagonal directions. So here we will find another value here by 1. So we have now 2. So if you stop by 1 or the previous one, does any other pixels for the 8 connectivity have similar values equal to 1? No, in this case. So the maximum zone that we could capture is 2. So we will go to gray 1 or gray level 1 at zone 2 and increment that cell. For the second pixel, which is 2, we will try to find the maximum zone that we can achieve or capture in the 8 connectivity. So the 2 here has a neighbor here with an equal value 2. And this one or this value has another neighbor here and another one here and another one here. So you may ask, are we doing that for each pixel that we are going to? Yes. Once you capture a similar value pixel, then you assume that pixel as a search area and you are trying to find the neighbors in the horizontal, vertical, and diagonal directions. So once you stop here, you may say that I found another one here, but there is a duplication, so ignore it. So we have 2, another 2, another 2, there is another 2 here, 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 and here. So once you stop by a certain pixel with a similar value, then you are trying to find in the 8 connectivity, horizontal, vertical, and diagonal directions. The same here, there is another one here. Once you stop here, there are no more 2 values or pixels with the value of 2. Then the maximum region that we could capture at gray level of 2 equals 9. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So you go to gray level 2 at zone 9 and increment that cell. Move to the third pixel. You will find the value equals to 3. But there are no neighbors here with a value of 3. So it's only a zone of 1. So go to gray level 1, add zone of 1, and increment that cell. Once you stop here, you cannot proceed with that 2 value because simply this value was seen. If you remember in the GLRM features, we said that once you stop by a pixel that was seen, you cannot proceed with that. So just ignore it. So ignore this value. For this pixel, we will check any other pixels with the same value. For the 8 connectivity, we will find this one and then this one. So we have a zone of 3 at gray level of 1, so we'll increment that cell. After that, we will encounter 3 with a neighbor here, so we have a zone of 2 at gray level of 3, so we'll increment that cell. We will skip this one, and this one because we have counted them in our zones and we will get that 0. It's 0 with a zone of 1, so we'll increment that cell. After that, there is another 0 here, and no neighbors with the same value, so we will increment the same cell by 1, so it will be now 2. After that, we will skip all of those because they were seen, and we will go to this pixel. We will check the neighbors, this one, and this one. So we have a gray level of 1 at zone of 4, so we'll increment that cell by 1. After that, we will skip this, and go to 3. It's a zone of 1, so we'll increment that cell by 1, so it will be 2. The last pixel will be 0 at zone of 1, so we'll increment that cell by 1 after ignoring all of those because they were seen. So the idea here is simple. We have a matrix. We are looping on each pixel. We are capturing if this pixel was seen or not. If the pixel wasn't seen or new, we will check all of the neighbors for the specified connectivity, which is in our case 8 connectivity. After we complete and find the maximum zone, then we will increment the size zone matrix by 1 in the specified gray level and specified zone. So to be able to do that using scripts, we can specify some rules that we can follow so that we can fill the size zone matrix. The first, we are checking that the current pixel value and neighboring pixel values should have similar values. And before checking the neighbor pixel, we need to verify the lower and upper boundaries so that we cannot get outside the specified boundaries. Also, we must ensure that each visited element or pixel is not revisited. And this can be solved by the same matrix as we did with the GLSZM matrix. And to do the same function for each pixel that we are going to visit, then we can handle that using recursion because we are doing similar operations at each visited pixel or element. Imagine we are here, we will do the same checks, the 3 checks that we mentioned. If we go here, we will do the same checks, the same here, here, and here. We will do the same checks. So we can set a function and apply recursion to handle that branching and to find the regions based on the given connectivity 4 or 8 for 2D and 6 and 26 for 3D. We can set a dictionary, an empty dictionary in our code that consists of keys and values. And the keys here are the gray levels, and the values should be lists. Inside each list, we will include the whole region or the whole captured region. How? Simply, when we go to the pixel and apply recursion and conclude that we got these 2 values, then we can include in the dictionary at the key 1 a list that consists of the coordinates of those pixels. So we have a zone of 2, 1 here and 1 here. So the region will be 1 and 1 for x and y, and 0 and 0 for x and y for the other pixel. So we have here a list that includes a zone of 2, and inside it 2 values. Each of them are the coordinates. When we go to the pixel, we have 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. So at grade 2, we can include another list that has 9 values. Each value is considered as XY coordinates for the pixel. We will do the same for the third and so on until we complete the whole searching. And when you encounter another region, you can append it into the list as another element. So we got earlier these 2 values at gray 1 and another here with a zone of 3 at gray 1. So we can include another element here inside the list. So we are going to append the new elements one by one inside each key or inside each gray level. By the end and the completion of the whole matrix, you can conclude with this dictionary, the keys and the different lists, and in each list there are elements and each element is considered as a region. Using this dictionary, we can fill the size zone matrix. How? It's simple. We go to each key, for example, gray 0. We count each element in them or each set in them. We will begin with the first set. It consists of one element or one tuple. So we will increment the cell at gray 0 at zone 1 by 1. It's another set, so it will be 2. It's a third set, so it will be 3. Let's go to gray 1. We have a set, another set, a third set. The first set consists of 2, so increment that cell. A second set includes 3, so increment that cell. The third includes 4 elements, so increment that cell. So we have here now 1, 1, 1 and in each cell. For that, they are 9 connected. So at gray 2, at zone 9, it's 1. For the last one, we have 2 sets, in each of them 1 element. So we have here 2. Here we have 1 set with 2 elements or a zone of 2. So increment that cell. So the situation is simple. Create a function. Use this function to make recursion. For each iteration or each check, you are not outside the boundaries. You are checking that the neighbor and the current are the same intensity and the pixel is not revisited. Then append the dictionary that consists of keys and values. Check the key, append into the list for that key with the different coordinates or the zone coordinates. By completing the whole dictionary, then you can fill the size zone matrix one by one by checking the size of each set inside the list and fill the corresponding zone. So let's start coding. Go to script number 17. Inside it, we have defined a similar matrix similar to the matrix we defined in the slides, and then converted this matrix to a NumPy array for easier processing and mathematical operations. Then we set the connectivity type 4 or 8. We set it here 8, similar to our example. Then we executed a function called calculate size zoom matrix and gave this function A and C. A is the NumPy array or matrix and C is the connectivity. And this function is added to the helpers file. If you go to the helpers file, you will find 2 functions for the size zoom matrix. One is called 5 connected regions and another called calculate size zoom matrix. This function, which is called calculate size zoom matrix, will execute the find connected regions. How? Inside this function that accepts the image and connectivity, apply normalization or not, ignore zeros or not, and they are set by default to false. This function, it checks first if it's an image, if the connectivity is 4 or 8, if the size of the image is not 0, and it's not black. If all of these conditions aren't met and we have a good matrix, then we can proceed. How? Here we are getting the dictionary that we described from a while that consists of keys and values, and the values are lists, and each list has a set of sets. Then, based on this dictionary, we are building the size zoom matrix. How? We mentioned that we need n by z matrix that's filled initially by zeros, which is here. So what is the size of n? What is the value of z? N is its discrete values. We calculated it multiple times by getting the minimum and the maximum and incrementing 1 after subtracting both of them. And z here should be the width multiplied by the height for 2D and multiplied by the depth for 3D. But if we did that, we will consume much memory. How? Assume that we have 512 by 512 image, so we'll multiply in width 512 by 512, 512 squared, so it's big matrix. And as the matrix doesn't have a single color or a single intensity, so the whole matrix or the rest of the right hand side of the matrix will be filled with zeros. Instead, we can do a simple trick to save memory. How? By simply getting the maximum length of the maximum set by looping on each key, getting their values, which are lists, and looping inside each list, the sets I mean, and getting the maximum length of the set that consists of the highest number of elements. So here we are getting the length of each zone in each value, which is a list for each zone, and adding them in a list and finding the maximum value. Assume here it's 9 or 10, so z will be 9 or 10. If you remember, I mentioned at the beginning of describing size zoom matrix that z should be 25, but I set it to 10. Why? because as I wanted to save space and to emphasize the importance of doing that. Instead of getting a matrix with 25 in width, I set it only to 10. So I saved about 15 cells or 15 columns. So the trick here, get the length of each zone, get the maximum value. This will be the Z value. Tell zeros for the size zone matrix. After that, iterate over the dictionary. Check here. The current pixel is the key. The values called zones, which is a list. Loop on each set of the sets inside this list. Check if you need if zeros should be ignored or not, and the current pixel is 0, then ignore that. Otherwise, increment the cell given the zone and given the current pixel value, which is the gray value in the size zone matrix. After iterating all over the dictionary, calculate the summation. If the summation is 0, and this means that all of the cells are zeros, no one of them, no cell is incremented, then return. Otherwise, check if you need to apply normalization, divide by the summation, and add a small value to avoid division by 0, just in case. And finally, return the elements, the size zone matrix, the size zone dictionary that we built, N and Z values. And here, we need to ask how to calculate the dictionary. This dictionary is the output of the find connected regions, which is the first function here. So what is inside this function? This function first accepts image and the connectivity. Image is the whole image, the connectivity 4 or 8 if you are dealing with 2D, and here we are doing so. Then we created a recursive helper function inside this function, and let's skip it for now until we complete the rest of the find the connected regions function. Then we create a scene matrix, which is an empty with a shape similar to the image shape. Then we created the regions dictionary, initially empty. Then we looped all over the image. Then we are skipping if this pixel is seen, and this means it has a value of 1 inside the scene matrix. Then if the pixel is not seen and not skipped, then we are getting the current pixel. We are checking if the current pixel is not in the regions, and this means that because the dictionary is empty, then we are creating an empty list with the current pixel value inside the regions dictionary to fill it with an empty list. After that, we are creating a set. A set in Python has a benefit. It avoids duplications. So if we added 1 and 1 as a coordinates multiple times, the set here removes any duplications or avoid any duplications. This set should include all of the coordinates that create the whole zone. So how to do so? Simply by giving all of these parameters to the recursive helper, and the recursive helper should find the maximum region by recursively iterate all of the pixels under specific conditions. So we are giving here ij, the current pixel, which is 1, 2, 3, any value, the region, which is initially set as an empty set, the scene matrix, the connectivity 4 or 8. Assume that the recursive helper function completed its execution, so the region here should by the end be filled with the region. So we are checking here if the length of the region is above 0, then this means we got a region not empty. Then we are appending it to the list that was created initially here. After completing all of the pixels and iterating all over them, then we are returning the regions. So what does this function do? Open this function that accepts ij, which are the coordinates, the current pixel value, the region, the scene matrix, the connectivity. Inside it, we are doing something simple. We are doing some checks and then adding the current pixel coordinates to the region, setting to the scene matrix and flipping its value to 1 because the pixel is seen. Then we are doing multiple other recursions, and that's it. So the benefit of this function is to bend to the region and flipping the scene matrix at these coordinates. So what are these checks? We are checking, as we mentioned, that we are not outside the boundaries, and the current pixel has the same value to the neighbor pixel, and the I and j are not seen already. If any of them or any of these conditions aren't achieved, then we are returning to stop the execution of this branch. So if all of the branches stop the execution, then the recursion for this pixel will be stopped, and by the end, as we mentioned, the region set will be filled with the whole region or the maximum achieved region. What about these calls? We are calling the same function with the same parameter, but here we are changing the coordinates or the neighbors, up, left, down, right, or horizontal and vertical directions. And if you are using 8 connectivity, then we are already have 4 of them, and another 4 if we have a connectivity value of 8. Then we are doing that for the diagonals, top right, top left, bottom right, and bottom left. Then if C is 4, this will be executed only. If C is 8, then all of those will be executed. Again, by the end, then the region set will be filled, and we are appending it to the list. By doing that all over the pixels, then we have a final dictionary that can later fill the size zone matrix. And it worth noting, or you may ask, why this function doesn't return anything, and you are saying that this region will be filled. Simply because here we are referring in Python by reference, not by value, because we are passing an object. Objects are passed to the function by reference. So if you are referring here, then you are not creating another variable, but instead you are referring to the same location in the memory. So this region variable will be filled, which was initially set here. So by the end, this region object is the whole container that consists of the coordinates. Similarly, the same matrix, we are passing it and filling it by reference. So if you are passing an object in Python for the function, then you are doing that by reference. If you are passing a single value or a singular numeric value, such as connectivity, it's called by value. And I'm illustrating this just in case you may mention that this function doesn't return anything. Now we have illustrated these two functions, which will return a size zoom matrix and dictionary. In the values, you can now print them. After executing the code, you will find something like that. These are calculated matrix, and these are the output of the script. The matrix, the dictionary, which looks like the dictionary we created earlier, and this will be the size zoom matrix. You can double check 2, 1, 2, 1, 3 here, 3 here, 1 here, 1 here. And if you tried again to run the code, but with connectivity of 4, you will reach with a size zoom matrix that looks like that. And this is our 8 connectivity. Now it's your turn. This is a matrix, and we need 8 connectivity. Now you can do hand calculations to create the size zoom matrix and validate your results with the code to check if you are doing correctly or not. So you can pause the video and do so. Once you complete, this will be your matrix, your size zone dictionary, and your size zone matrix for the given 8 connectivity. Once you computed the size zone matrix, we can now measure a set of statistical size zone features. And these features provide insights into the texture and the structure of the given image. And these are the first 5 features: small zone emphasis, large zone emphasis, gray level non-uniformity, zone size non-uniformity. If you remember, in GLRM, we mentioned something like that, such as the small run length emphasis and large run length emphasis. And the formulas here look similar to the formulas with the GLRM, but here they depend on a different matrix and they have different meanings. For example, the small zone emphasis, they measure the distribution of a small zone, and for the large zone, they measure the distribution of large zone. And for gray level non-uniformity and zone size non-uniformity, both of them measure the variability and uniformity, one for gray level and another for the zone size. And the zone percentage is the ratio of the number of zones to the number of pixels. The second 5 features are gray level variance and zone size variance. And here we are measuring the variance in gray level and zone size. Then we have zone size entropy. And here we are measuring the randomness in the distribution of zone size. Then we have low gray level zone emphasis and high gray level zone emphasis. Here we are measuring the distribution of low and high gray level respectively. The last four features are mix between the zone and the gray level. So here we have a small zone, low gray. So we are measuring the distribution of a small and low gray level zone. For small and high, we are measuring the distribution for a small zone and high gray level. The same for the other two, large zone, low gray, and large zone, high gray. So let's start by the first example for the small zone emphasis. This is the corresponding formula for it. So I and j are counters or indices. Ng is the number of gray levels, and Ns is the number of size zones, and N here is the sum of the matrix, which is a size zone matrix, and equals to 3 plus 1 plus 1 plus 1 plus 1 plus 2 plus 1 equals 10. And P is the probability or the normalized value of the size zone matrix. And here, for simplicity, we will ignore the normalization. And J, as mentioned, is a counter or index. So the formula is dividing each value of the probability or each value in the size zone matrix by J square. So here we are setting a counter I from 1 to 4, and here from J to equals 1 to G equals 9. So for this formula, we are getting each value and dividing it by J square. So 3 divided by 1 square, 2 divided by 1 square, 1 divided by 2 square, 1 divided by 2 square, 1 divided by 3 square, 1 divided by 4 square, 1 divided by 9 square. Sum all of that, divide by 10, you will get that value. Another example for large zone emphasis, we are multiplying the value of the probability or the value in each cell by J square. So we are getting each value and multiplying by J square here. 3 multiplied by 1 square, 2 multiplied by 1 square, the same until you reach 1 multiplied by 9 square. Sum all of that, divide by 10, which is the value of n. It will equal to 11.9. What about small zone high gray level emphasis? We are multiplying by I square and dividing by J square. So simply, if you need to get the small, then you are dividing. And if you need to get large, then you are multiplying. So for small zone, we are dividing. Dividing what? Dividing J, because J refers to the zone. High gray level, high means multiplication, so multiply by I. So what about large zone, low gray level emphasis? Then you are multiplying by J square because large zone. And for low gray level, we are dividing by I square. So this is simple. So in this formula, we are multiplying by I square and dividing by J square. So 3 multiplied by 1 square divided by 1 square. And for this one, 1 multiplied by 3 square and divided by 9 square. And for this one, 2 multiplied by 4 square divided by 1 square. The same for the others. Sum all of them, divide by 10, it will equal around 4. Now we need to write a script to calculate all of that automatically. Refer to script number 18, GLSZM features example. We defined at the beginning the necessary libraries and the matrix, and then convert it to a NumPy matrix, defined the connectivity, calculated the zoom matrix, got the matrix and the dictionary. Then we started to calculate the different features, as we did with the GLRM in the previous lecture. What we did here, for the size zoom matrix, we need to divide by J square. J refers to the size zone, which is the Z variable. So we are getting the matrix, dividing by a range from 1 to Z squared, and adding a very small value called epsilon to avoid any division by 0, and then summing all of that and dividing by n. N here, or SZN, refers to the summation of the matrix, which was in our example equals 10. Next, for the large zone, we mentioned that large means multiplication and small means division. So here, instead of division, we are applying multiplication. What about gray level? For the gray level non-uniformity, if you return back to the formulas, it's squaring according to ns, and here we are squaring according to ng. Here for the counter of size zone, and here the counter for gray levels. To do that using scripts, we are summing the square of the matrix according to axis equals 1 and here axis equals 0. After that, we are summing all of the matrix or all of the result and dividing by n. For the zoom percentage, we are dividing n by the product of the shape, which equals to the elements in the matrix. For the variance, as defined here and here, we are multiplying the probability by the counter minus the mean squared, and here j minus the mean squared. To do that, we are simply multiplying the matrix by I minus the mean squared, and here j minus the mean squared. For the entropy, first we calculated the log with base 2 for the size zoom matrix, and we added that to avoid any log of 0. Then we replaced any negative infinity with 0. After that, we replaced any negative value with 0. After that, we multiplied the log value by the matrix and then summing all of that and dividing by n. And this is reflected by this formula. For the low gray level and high gray level, we mentioned low or small means division and high or large means multiplication. So here we are dividing by the range from 1 to n, and here are multiplying instead of division. Then for the small zone, low gray level and its alternatives, we are multiplying and dividing according to small or low or high and large. If you encounter small zone, then divide by z or the range of z. Low gray, then divide also by the range of n or from 1 to n, as we did here. For example, large and high means multiplication of both of them. Large and low, large zone means multiplication of the range of zones, and low gray means division by the range of n, and the same for others. After that, we rounded each feature to 4 decimal points and printed them. When you execute the code, you will get the following results. You can validate the results. For example, for the large zone emphasis, it's 11.9 as we calculated it here. And for small zone high gray level emphasis, it's around 4 as we did here. Now we need to apply the same for 2D images and 3D volumes. Similar to what we did in the previous lectures, we need here to get the mask, the image, apply bitwise and to get the ROI, which is here, and then apply bounding rect to remove any surrounding black areas to get the cropped image, and then we need to apply the size zoom matrix and extract the features from that cropped ROI. Before beginning with applying the feature extraction using size zoom matrix to a 2D image, it was noting that we encapsulated the feature extraction using the size zoom into a function here that accepts the size zoom matrix, the data, which is the 2D image or the matrix, and n and z values, and inside it will start to calculate similar features as we illustrated from a bit, and then returns all of that inside a dictionary without any rounding. You can round these features later, and as we are using recursion to avoid any recursion error using Python for large images, for example, if you are using 512 by 512 image, then we are increasing the recursion limit, as the default recursion limit is 1000. So we are setting it to 10 to the power of 8 using the sys library and the set recursion limit function. So if you are using or applying the size zoom feature extraction on a large image, don't forget to include this. Otherwise, you may get a recursion error during the execution of the code. So go to code number 19, import the helpers and numpy cv2 os, and then here we defined the paths. It checked if both of them exist. Then we read both of them in the grayscale image. After that, we applied bitwise and to inspect the ROI. Then we applied the bounding rect to get the coordinates xy, width and height. Using these coordinates and width and height, we got the cropped region. Then we checked if that cropped region is below 0 This means that the image is empty, then raise an error. Otherwise, the code will continue. Set the connectivity, then calculate the size zoom matrix. And don't forget, as you are dealing with an image, to set its normalization and ignore zeros to true. Then, using that matrix and N and Z values and the data or the image, which is grouped here, we calculated the features, and these features, the dictionary. After that, we printed the connectivity value and the features rounded to 4 decimal points. When you execute the code at 8 connectivity, you will find these results, and for 4 connectivity, you will find these results. After that, we need to apply the GLSZM features on a 3D volume. We mentioned at the beginning of this lecture regarding the connectivity, if you are dealing with 2D, we can use 4 or 8. 4 means horizontal and vertical. 8 means horizontal, vertical, and diagonal directions. And for 3D, we mentioned that we can use 6 or 26. Simply, how we determine this number. If this is a slice, this is a forward slice and this is a backward slice, or pre and post slices, then simply, if we need the horizontal and the vertical, as we did with the 2D, then we can consider this direction, and this direction. So 1, 2, 3, 4, 5, 6. What about if we need the diagonals or include the different diagonals? Then simply, if you have a pixel here, then you are counting all other pixels. We have 3 slices. Each contains 9 pixels. So 3 multiplied by 9 minus the current pixel. So the value will be 27 minus 1 equals 26. So if you need to include other diagonals or other directions, you need to apply 26 recursions. If you need to apply only horizontal, vertical in the 3D, then you have 6 pixels. So to do so, we need to emphasize again that we need to apply padding to unify the different shapes, as each grouped ROI in each slice may have different shapes in width and height. As you see here, different widths, different heights. So unifying the padding will avoid any out of bounding errors. And the unification here means adding black regions around the grouped ROI, keeping it in center. Now go to script number 20, GLSZM features for 3D. We imported the necessary libraries, and don't forget to import the helpers file. We began by setting the bases for the different slices. Then we use the defined read volume function to get the volume grouped, and we illustrated that function in a previous lecture. Then we set the connectivity to 6. We have the option to set 6 or 26. Then we executed a similar function to what we did in 2D called size zoom matrix 3D to get a size zoom matrix and the corresponding dictionary and N and Z values. And then we used the defined size zoom features by passing the volume or data and the size zoom matrix, N and Z values, and get the features. By the end, we printed the connectivity and the different features rounded to 4 decimal places. So how this function works? This function can be found in the helpers file. Here we added another 2 functions called, one is called find connected regions 3D and another called calculate size zoom matrix 3D. They are similar to the 2D versions, but here for 3D. What we did here in the size zoom matrix 3D, we updated it to handle the connectivity of 6 and 26 with the same flow. We checked it's a 3D volume. We checked the connectivity. We checked the shape, the maximum value in the volume. Then we executed the function find the connected regions 3D to get the dictionary. Based on the dictionary, we started to get N and Z values. We created a size zoom matrix, and using a similar flow to the 2D version, we filled the size zoom matrix, checked the normalization, and here we checked for ignore zeros, and finally we returned the 4 variables. So this function is similar to the 2D version, but instead of 2D, we here executed the 3D version, and instead of 4 and 8, we added here 6 and 26, and instead of 2, we added here 3 for volumes. Now let's go to this function, find connected regions 3D. Here we accept the volume and the connectivity, and we added also here a recursive helper function. Again, we mimic the same flow of the 2D version, create a C matrix, the regions dictionary as an empty dictionary. And instead of using only 2 for loops, we here used 3 for loops. We checked if it's seen, get the current pixel. It checked if the current pixel is not in the dictionary. We added a new list, an empty one, with the key of the current pixel value, created the region as an empty list, executed the recursive helper, and here instead of using only I and j, we are here using I, j, and k. And then here I checked if the region is filled. If so, we appended it to the list, and after doing the same process on all of the pixels and regions, we are returning the different regions dictionary. Inside the recursive function, which is here, we are handling the 6 or 26 neighbors pixels. So at the beginning, we added the condition to stop the branching of the recursion. It checked the boundaries. It checked if the current pixel is not similar. It checked if the pixel is already added in the region and if it's seen or not. If any of these conditions is met, then the return statement will be executed. Otherwise, the coordinates will be added to the region set, and you will change the C matrix at these coordinates to 1. After that, we applied recursion, a set of recursion, whether you're using 6 or 26. For 6 connectivity, we have only 6 recursion calls, and if it's 26, then there are more 20 calls are remaining. 6 are here, and the rest are 20. Here, for the same slice, 4 pixels, and here for the pre-slice, 8 pixels, and here for the post-slice, another 8 pixels. If you sum all of that, you will reach here 20 plus 6, you are getting 26 calls. Now, these 2 functions are ready and called here. If you execute the code, you will find the following results for 6 connectivity and these following results for the 26 connectivity. So, in this lecture, we have covered the gray level size zone matrix, and we mentioned that we need 2 steps. One, to calculate the size zone matrix, and based on that matrix, we can calculate different features, such as the small zone emphasis and large zone emphasis. Then we applied that on a simple matrix and a 2D image. After that, we presented how to calculate the size zone features for a 3D volume.